In these reactions, you see O3 as your first step, and DMS, which stands for dimethyl sulfide, as your second step. And that's a sign that you'll be doing a reaction called ozonolysis, or sometimes it's also called oxidative cleavage. The cleavage is actually contained in this lysis. Lysis means to break things apart or to break things down. For example, if you break ideas down, you have an analysis. And so lysis is just telling you you're breaking something apart. And that's where this reaction is a little different from the other reactions in this addition reaction chapter. Because what you're breaking apart in this reaction is the double bond. So you're sort of karate chopping that double bond. And the two places that are left, the two pieces that are left, instead of those carbons bonding to each other in a double bond, they bond to an oxygen. And so you could see how that place where we broke that double bond creates two molecules. One molecule that's sort of on top, one molecule that's sort of on the bottom here, and that's two separate products you'll get. And in each of those products, where you had the double bond between carbons, you now have a double bond to an oxygen. That's the general idea of what's going on here. You'll notice in these products there are only two oxygens, but there are three in the recipe in ozone. And that's what the second step is for. The dimethyl sulfide sort of mops up and removes the third oxygen in this reaction. And so those would actually be your products for this particular reaction of ozonolysis. You would have these two products as your products. So those are two separate molecules as your products. You could, especially if you're just beginning, you could leave them like that. You might like to train your mind to sort of write them in standardized ways. So have the oxygens on top. But those would be your two products for that particular reaction. We can try to do this with a ring, and I think that's a good example of where this reaction can be very useful. Rings are relatively rigid. The bonds are not able to rotate 360 degrees. So they're incorporated into a lot of hormones and neurotransmitters and medications. But sometimes you don't want something to be that good of a medication, or you don't want it to be so biologically active. For example, one of the reasons why people get so addicted to morphine is because it has a bunch of rings and it fits very reliably into a receptor site. And if someone who is addicted to morphine suddenly stops taking morphine, the withdrawal symptoms can be so bad as to even cause them to die. And so you want to find a way to make morphine slightly less addictive as you are sort of weaning people off of it. And one way you do that is with a molecule called methadone, which is morphine, but where you've broken one of the rings. So now that molecule does fit into the same receptor site as morphine, so the withdrawal symptoms are not as bad as they would be if you just stopped taking morphine. But it doesn't fit into those pockets very reliably because you don't have as many rings, so the bonds are rotating and they don't have the right shape to fit into the pockets as often. So it's a sort of way to change the strength of a chemical messenger, is to break break rings. And the molecule after the ring is broken won't fit into a receptor site quite as well. So one way you can break rings is with ozonolysis. So you see the double bond, you see ozone, O3 as your first step, dimethyl sulfide as your second step. That's a sign that you're going to be karate chopping or breaking that double bond apart. Now at first, when you redraw it, you can redraw it much like it is already. But instead of having the two carbons double bond to each other, they would be double bonded to an oxygen on each end. you can see how that's very similar to the last example we did. You're just cutting that double bond apart, and where the double bond is broken, it goes to an oxygen on each carbon. So each of those carbons in the double bond is now double bonded to an oxygen, instead of being double bonded to each other. Now, with these rings, you don't want to leave the molecule like this, because it's a very non-standard way of drawing this. Especially on a standardized test, they would never draw the molecule quite like this. So you want to be able to think of how these straight chains might look in different ways, and to be able to associate those pictures with a prediction you make like this of the product. And I think the most useful way to translate between these almost ring-looking things with straight chains is to number the chain. Now, this numbering is not like numbering for naming. With naming, you have to be very careful about which end you start numbering from, for example. But in this case, we're just numbering the backbone so that we can keep track of where everything is. So just to keep track of everything, I'm going to start numbering at the top here. I'm going to work my way around this molecule. I can see that there's 7 carbons. So when I try to redraw this molecule in a more standard way, I'm going to draw 7 carbons. So here's 1, 2, 3, 4, 5, 6, and 7. And just so I can see the connections more clearly myself, I'm going to number each of these. So 5, 6, and 7. Now, as you're comparing this straight chain, this very standard way of drawing a straight chain, with the molecule we had a second ago, you'll notice that you have a double bond to an oxygen on carbon number 2. So we can fill that in. On carbon number 2, put a double bond to an oxygen. So that corresponds to that double bond on the straight chain. Likewise, we could see that on carbon number 7, we have another double bond to an oxygen. And so on carbon number 7, we have another double bond to an oxygen, and those correspond to each other. So really, the standard way of drawing this molecule would look something like this. And that would be the way you would want to draw it on a test. You would want to draw these sort of rings having been broken open, and you would want to draw them in the more standard way of drawing them. So this ozonolysis is one kind of unusual reaction because it's the only reaction in this chapter where you don't just add two things onto the carbon chain. Instead, you break a double bond. And on each side of that double bond, on each carbon on that double bond, you have a double bond to an oxygen in its place. And one very common thing this can do is it can break open rings. And you can see how you can translate from a broken ring to a standard way of drawing it by numbering that carbon chain. And hopefully this video has given you a little bit of practice in predicting those products for this ozonolysis or oxidative cleavage one-step synthesis when they give you all the reagents.